Thank you very much for that introduction. I did promise my brother that the first time I presented about UBiKuity, I would tell everyone that he came up with the name, not me. Uh, so yes, there you go. Thank you, Nick. Uh, so yes, I'm going to be talking about this library that I developed over the last year and a half, 2 years or so, that is a tool to analyze particle motion in Earth's magnetosphere. And I think we'll start with a little bit of background on what I mean by that. But the broad theme of this talk is my experiences in trying to write good scientific software, trying to write a large code for the first time as somebody who's almost entirely self-taught in terms of software engineering, and the sort of problems, difficulties, learning experiences that I came across in this process. So I think I found this looking at this little short text called epigrams in programming the other day that you might have come across, but it's quite fun. But I thought the best one I could find for this was everything should be built top down except the first time. And unfortunately, you have to do things the first time once. So, and we'll see the problems with that during this talk. Oh, it's full of the Earth as well. Okay, so I'm going to be talking about charged particles trapped in the magnetosphere. So there's a few ways to look at the physics of charged particles. So the most obvious one is to look at the Lorentz force, which is that equation up on the right there. So it's the force on a particle, on a charged particle, with charge Q due to the electric field E, and the force in the magnetic field B, which and the magnetic field. So in order to work out what the particle is doing in terms of the Lorentz force, you need a magnetic field. So there's a model of the Earth's magnetic field. The sun is somewhere off down in sort of the bottom left, down. There's a mouse mark? No, there's a mouse, yeah. The sun's somewhere down here, and it's compressing the front of Earth's magnetic field, and you get this big tail that extends out way further than I'm showing here. But you get this very complex magnetic field that's an interaction of the internal magnetic field in the Earth generated by the core, which is sort of like a bar magnet, like a dipole magnet, and then various current systems that come from charged particles coming off the sun, and charged particles trapped in this magnetic field itself. So the magnetic field is complicated. There's also an electric field. So here I've just drawn, because if I drew both the fields in their full glory, it would be completely uninterpretable. This is bad enough. But this is the electric field in the equatorial plane, or electric equipotentials in the equatorial plane. But you can see that there's some serious structure there as well. So the point is that both these electric and magnetic fields are not trivial. They're quite complex, time-varying fields. And so the result of treating the particles with Lorentz force gets quite complicated quite quickly. So this is an example of the particle path. So yellow is a particle, and the red are magnetic field lines. This is just, now we're just in a dipole, so a much simpler magnetic field. But you get effectively three types of motion that come out of Lorentz force. In a magnetic dipole, you get gyration around the field line. You get this bounce motion where you go up and down the field line, and then you also get a longitudinal drift around the Earth. So you get these three periodic motions that combine together to create these sort of torus-shaped orbits, wiggly torus-shaped orbits around the Earth. And that's just a magnetic field. You also get, the electric field, you get an additional sort of longitudinal drift component that's energy dependent. Yeah, so the point is that the Lorentz force, these particles are doing quite complex paths. They're moving in, predicting the motion for the Lorentz force is very computationally expensive, and you end up with difficult to analyze paths. There's some various tricks you can do to sort of reduce the parameter space you're working in a little bit. But I just want to give you a sense of the complexity of the problem, and yeah, the range of possible behaviors you can get out of quite a simple system. So there's an alternative way of looking at how the particles behave. So back in 1978, a man called Eldon Whipple pointed out that he wrote this paper saying, okay, well, instead of treating the particles, talking about particles' position and velocity, we'll just talk about its Hamiltonian, which is the sum of its kinetic energy and potential energy. So in this case, H is the Hamiltonian, mu is the magnetic moment of a particle in the magnetic field. Bm is, well, we can think about that as the local magnetic field strength at the particle, effectively. Q is its charge, and U is the electric potential at the particle. So this first term here, mu Bm, that's effectively the kinetic energy. The second term is the potential energy. And the sum of the two remains constant. So mu is constant, Q is constant, B and U vary, but they vary in such a way that H, the Hamiltonian, the total energy, remains constant, as long as you don't have other things coming in the system and interacting with particles. So a little bit of rearranging of this, we can get Bm in terms of everything else. We can differentiate Bm with respect to U. And from that, we can see that the rate of change Bm with U is just the ratio of these two constants. So dBm by du is constant, effectively. What that means is if you make a plot of potential versus magnetic field strength, U versus Bm, the particles are going to move in straight lines through the space, which is much simpler than the crazy wiggly torus we had before. So this offers a sort of a very nice way to simplify the range of possible particle paths that we can get in a sphere. But then the main question is, okay, the particles move in straight lines, but which straight lines? Are they bounded? Like, where are they going? So the main purpose of ubiquity is to work out the bounds of which straight lines in UB space are allowable. So on the left plot there, we've got a plot of the path of a particle projected onto the equator in sort of Cartesian space around the Earth. And on the right-hand side, we've got the equivalent path as a red line in this UB space. And the black curves effectively denote the allowable space of UB, U, and B values you can get in the magnetosphere. So there's some range of magnetic field strengths that are in the magnetosphere. There's some range of potentials. So the allowable pairs of U and B are represented by the space between those black curves. And what that means is that every single possible particle path within the magnetosphere is now just a straight line somewhere between these two curves. So the ones that touch both curves at either end, those are trapped particles. They're going in a closed loop around the Earth. The ones that go off either end, that go out the sort of that go out the end of this funnel, either end of this funnel, are particles on open drift paths. So they're coming into the magnetosphere in some place and going out somewhere else. And if we look at this graph, we can get a few different bits of sort of intuition about the particle behavior. So on the x-axis, the magnetic field strength. The magnetic field strength is higher the closer you get to Earth. So the right-hand side of this, where it cuts off, is the surface of the Earth, effectively. So particles that go off the right-hand side are drifting into the surface of the Earth. And effectively, what they'll hit first is the atmosphere. They'll be lost to the atmosphere. They'll, interact with particles in the atmosphere and lose energy, and we don't care about them that much. And then on the left-hand side, we've got low magnetic field strength. That's large radial distances far away from the Earth. And those are particles that are being lost to the boundary between Earth's magnetic field and the solar wind, the interplanetary field that's coming from the sun. And because the equation for the straight lines the particles follow is determined by this ratio Q over mu, where mu is the particle magnetic moment, which is dependent on its energy. Low energy particles go in sort of horizontal lines across the space, and high energy particles go in vertical lines across the space. So we can, effectively what we can see here is that low energy particles are much more likely to be on open drift paths because they can go out either end of the funnel. Whereas high energy particles go straight up and down. It's much more easy for high energy particles to stay trapped. And why do we care about all this? Well, the eventual point is to create a model of Earth's radiation belts, which are these populations of really high energy charged particles trapped in the magnetic field. So this is a visualization of the radiation belts. The color sort of denotes the radiation intensity, the number, in this case, the sort of density of electrons that are given energy at a different point in space. And you can see there's various satellites here, GPS satellites, satellites in geostationary orbit that go through orbits that are that can intersect the radiation belts. And that can be quite a big issue for satellites because it's a very high radiation environment. You can get damage to satellites, you can get degradation of the solar cells, you can get single event upsets in the computer, or you can get build up a static charge that discharges and creates big sparks and discharges that damage your components. So being able to predict and model the radiation belts is very important for understanding sort of what sort of lifetime different satellite components will have. And also some interaction with the atmosphere can cause increased or decreased satellite drag, so especially in low Earth orbit. So in order to maintain active satellite infrastructure, we need to have a really good understanding of these charged high energy particles. And I mean, as I'm sure everyone knows, in the modern day, that's increasingly important. We've gone up from something like 1,000 satellites in, I think it was 2015, about 1,000 active satellites, and now there's, I think last time I checked, there were over 6,000. So yeah, the modern infrastructure is increasingly reliant on a good understanding of the near Earth environment. And there are existing models of the radiation belts. This is not something that I stumbled across and thought nobody's worked on. But there's various restrictions that people put in place to try and simplify this problem. So most people make models that consider only a single species of particles, so only electrons or only protons, or maybe they assume there's a dipole field, or they assume the electric field has no effect. The advantage of this Hamiltonian method is that I can include realistic magnetic fields, I can include the effects of electric fields, and I can model any species of particle and any energy of particle, whereas previous models are often restricted in any or potentially all of these benefits. They don't have them. So yes, hopefully the end goal was to have a full model of the full range of charged particles trapped in the magnetic field in a single formalism, effectively, which nobody else has managed to do before. And those of you paying particular close attention might have noticed I said this idea came up in 1978. And I think the reason nobody's really tried to put this together is because up until now it's been completely computationally intractable to use this approach for realistic magnetic and electric fields. There's been 3 or 4 papers published in the intermediate time looking at very simple dipole magnetic fields, but nobody's looked at the general case yet, simply because it's computationally it is quite intensive. So to try and solve this problem, I put together, I'm in the process of putting together UBiKuity, which is a library of Fortran subroutines and functions which implement various numerical models that I need to model these systems. Around that, I'm developing at the same time a Python wrapper for generating inputs and parameters to the field models, and also handling various inputs and outputs of the physical models. And it's intended for use by me in my research. I'm currently trying to write a paper, the first paper that actually uses this. And it's also intended for others in my research group who are using subsets or the whole of the code that I've currently developed. And the hope is eventually I'll release an open source software. Partly because I think there's a lot of interesting stuff that can be done with this approach, but also because increasingly publication requires open source software, which I think is a good thing, but it does mean an additional workload for scientists in terms of producing usable open source software. It's very easy to put something up on GitHub. It's very hard to actually have it be usable by somebody without you guiding them through it step by step. So when I came to put together this talk, I thought, how am I going to structure this? And I thought, actually, one of the first things I had to learn when I took on this project was actually learn to use Git properly, beyond the clone command. So I thought, actually, I'll just structure this as sort of a little wander through the Git history of the project, and I'll show you some of the kind of interesting commits that relate to problems I encountered or learning experiences or new sort of facets of software engineering that I had to teach myself effectively in order to get this to work. And I'm sure, because this is self-taught, I'm very proud of this code, but I am also simultaneously very aware that I've not structured it as well as I could have done. And I'm certain that I've missed a lot of important things and concepts in software development and engineering. So hopefully, I'm hoping that someone at the end might come up and say, "Oh, you should do it this way." But yeah, so to start with, learning to use Git um, was, yeah, I mean, this project represented a massive increase in the size and complexity of any code that I'd made before. Um, so I really did want to be a bit more careful with its development, and also because it was going to be collaborative. The idea is that other people might be using it, and they might want to make their own edits and things, getting an actual understanding of how to use branches, different branches and forks and things was developed. But it was not without its problems, I think. Just going back through the Git history when I came to make this talk, I discovered that learning to use Git had been a more fraught process than I remembered, based on some of my commit messages, reverting and removing git keep and then putting it back and deleting again. Anyway, but alongside this, I'll go through sort of where I got to with sort of physical modeling at each commit as well. Um, so the first step was trying to get magnetic field models working. So to try and get the B out of UBK. Um, and this effectively involved, luckily, there's various community models, reverse magnetic field out there, and a lot of them used, pretty consistently by the space weather community and the geophysics community for many, many years. Um, and happily, there are Fortran versions of most of the kind of commonly used ones available for free online. Um, but it did involve some digging through them and refactoring and optimization, and quite frequently uh, making them compatible with modern compilers as opposed to having to run Fortran 77 compilers alongside Fortran 90 compilers, because I really didn't want to try and fiddle with multiple different compilation steps. Um, yeah, so this is just a comparison to a few magnetic field models. So on the left, we've got a dipole field model, and this is the first time I got field line tracing working. So it's sort of integrating the equation of the field line through any given magnetic field model. The middle is the international geomagnetic reference field. So this basically tries to uh, represent the non-dipole, or the a realistic model of the field due to Earth's core, effectively, or due to geophysical effects within the Earth. Um, so it's quite similar to dipole, but it's a little bit tilted. It's off the center of the Earth, and it does have non-dipole components. So it's a spherical harmonic expansion with, I think, 16th order. I can't remember. It's quite high order. Um, but that gives you the internal model of Earth's fields, so the field due to internal processes. But to get a realistic model of the magnetic field experience in space, you need to have components due to the various current systems that flow around the Earth. So on the right here, we've got IGF 13 plus one of these external field models, which is the Sigonenko and Sitnov 2004 model. And that introduces a lot of distortion due to solar wind. So you go from this sort of dipole-like shape to something that has that squashed on the day side and drawn way out on the magnetotail behind the Earth. But yeah, one of the difficulties with this is that they all are defined in different coordinate systems. So I had to do a lot of messing around with trying to make fast and accurate and reliable coordinate transforms between 6 or 7 different coordinate systems. Uh, well, 6 originally, and then a 7th, which is a mag coordinate system, which I think it's taken about 3 or 4 days to figure out why adding a mag coordinate system would ruin everything else. I don't actually remember what the issue was. I remember being very frustrated when I wrote this commit message, but not what the issue was. Okay, so the next thing I wanted to address was this was the first time that I've written code that I really intended other people to use. And so one thing I wanted to do was, I mean, previously I'd had a little bit of experience with Fortran, but it's mostly been either editing somebody else's code or writing something very small that I would, compile on one computer and one computer only. Whereas this, I wanted to be open source and used by myself on my personal laptop or on the workstations at BAS or on the HPC or by other people in other groups. I needed to have something more robust than a tiny compilation script. So I had to learn to use CMake, which I was sort of just presented to me by a colleague as the best solution. So I didn't really explore that very much. Whether there are other, I'm sure there are other build systems available, but it seems fine. If a bit, I don't know. There's a lot of documentation. I didn't read most of it, but it did work. And with a bit of collaborative effort from Brad, who's another postdoc of my group, this is actually one of two commits by somebody else in the project so far. Was from Brad. We did manage to get it working on my Windows laptop, on his Apple machine, and on the Unix workstations, the BAS and the HPC, and various other things. But yeah, I'd never really encountered having to try and make code resilient to multiple different operating systems. Which, I mean, previously most of my development experience has been in Python, which mostly hides that from you and tends to work pretty reliably across different operating systems. Whereas Fortran, and I assume most other sort of lower level languages, do rely a little bit more on the implementation of compilers and things on different systems. Yeah, so at this point, I also from Brad, he helped me get used to using the visualization toolkit VTK, actually a Python wrapper for it, and which greatly upped my 3D rendering game, which was pretty essential to this project because we're working in this quite complex coordinate space, working with magnetic fields that are kind of distorted. So this is the result of field line tracing in TS4 field in glorious 3D with a nice little skybox in the background, which is it's 2 lines of code to get the Earth in the skybox. It's so good. Yeah. So that point I had actually much faster field line tracing. One thing you may notice is there's a lot more field lines there than there were previously. So yeah, various improvements to the Fortran code that I've written to trace the field lines led me to get some, I don't know, I think about factor 200 speed up at that point, which I think is more a comment on how bad my original field line tracing code was rather than how good the optimizations were. Yes, in fact, so on working with Brad and giving Brad this code, he was actually, so I was working on this sort of particle tracing and UBK space development. Brad just wanted field line tracing to do his side of the project. But there are other field line tracing codes available in the community, but we decided to use mine basically to battle test it, and eventually his project is going to integrate into mine anyway, so we thought it's best to start with that. Which basically meant that at that point I suddenly had realized that I had very little documentation. And despite noble intentions, starting with noble intentions and documenting the first few things I wrote quite excessively, I had almost nothing. So I ended up writing proper documentation strings, like going away and Googling what you actually need in a documentation string, and realizing that finding out that Python had type hints. So I've been working with Fortran for a little while. I knew that Fortran was a strongly typed language and Python's not. But the fact that Python has type hints, I think type hints are a great form of sort of inline documentation. And it was very helpful for me just going back in this now quite large body of code to look back and sort of know a bit more about what each of the functions of it and were expecting to get. One thing I did look into but didn't actually include was, so in the docstring, particularly for this parameters, suggestively named parameters argument, the docstring then includes what each of the parameters it expects are and their units. I did look into AstroPy has a sort of units library that effectively sort of forces your functions to be sort of strongly typed in terms of physical units. And I did look into and think about using that. I didn't in the end because despite the fact I've got some quite weird units, I don't transform them very much. And in the end, trying to get that rewrite all the stuff I had to conform with that, in the end, I didn't put the time in. But it's a potential avenue that I might pursue in the future if I do start to run into lots of bugs with incorrect units. But as that hasn't happened yet, as I've not made that many errors with units so far, I think I'm getting away with it. But yeah, and potentially at the moment it's basically just me, Brad, and one other person using the code. And everyone's been fine so far. But people start, if I do make it open source and people get confused, that might be something to think about. sort of additional layer of uh, well, type checking that you get in physical codes that you don't get perhaps in other types of code. Mm. Yeah, so this also highlights some of the difficulties I had with interoperability between Fortran and Python, which are not two languages that seem to like natively mesh very well. And the way that you have to do it is coerce both Python data types and Fortran data types into C-compatible data types, and then pass the C-compatible data types between each other. Which, yeah, there's multiple methods doing that. So there's various things like NumPy comes with F2Py, which promises to do this fairly automatically for you. I couldn't get it to reliably work across multiple systems, despite trying for a while. It probably does work across multiple systems, and I'm doing something wrong. But after tearing my hair out too long, I decided to look for other options. You can also directly write things in Python in the C implementation of Python. Um, I did. I tried that very briefly, but really, I couldn't understand it. I didn't have. I think my knowledge of C was too weak. Um, so in the end, the option I went for was Python as a C types library, which basically just lets you coerce Python data types into C types. And as long as you're careful, you should then have everything compatible between Python and Fortran. The difficulty is that then you want to sort of abstract that C-type coercion layer away from anyone who's going to use this code, basically. So I ended up writing the called C-type class to try and do that for me. And I'll come back a little bit later. Whilst I was looking at typing in NumPy, I was trying to work out better type hints, and I just Googled type hints NumPy data types, and the first result was this website, which is quite helpful, actually. Thank you, Jack. Yeah. So after Brad wandering down the several times and telling me that code didn't work, after the latest push that I'd put back on the repository, I decided it's time to try and actually check that the updates I was making weren't breaking everything. So I'd heard of unit tests. I never tried to write one before. So I tried to learn to use PyTests. I did learn to use PyTests, mostly. The issue I had with PyTest is that I still don't really understand what the right approach is for writing tests for numerical code, effectively. So, because what I found in the end was that I could test my field line tracing algorithm against like analytically solvable cases of field lines. But then I also don't know that I'm not usually working with analytically solvable field lines. I wouldn't be doing field line tracing. So in the end, I ended up writing a whole bunch of tests for the sort of properties that numerically correct field lines should have. Like the fact that every point is sort of in order in 3D space. There's not any sort of jumping around too jaggedly. But ultimately, I couldn't figure out. Originally, when I was writing ideas for this slide, I wrote down ultimately you can't write tests that guarantee numerical validity. I've changed that ultimately I can't write tests that guarantee numerical validity. It might be possible, but I couldn't find that many resources online either. Most of the unit test stuff was sort of more wasn't really about numerical codes and numerical methods. But this has helped. I mean, it does definitely mean that if I completely break things, this will tell me. But if I get what looks like a real field line but isn't the exact right solution, then I don't know a way of writing a unit test to check that, except for the case of just refusing a dipole. So, for instance, the issue I had was if I fiddle with magnetic field models and the output of magnetic field models goes wrong subtly, it might be within error for a single magnetic field model value at a single point in space, but it will use field lines that are completely wrong. I never really figured out how to deal with that with tests. Potentially, I just think that's not really what test-driven development is for. But yeah, so at this point, I had the magnetic fields, and at this point, I've managed to get electric fields as well. So rather than just tracing magnetic field lines For the electric fields, they're defined a little differently. They tend to be defined in terms of the electric potential at the surface of the upper layers of Earth's atmosphere, the ionosphere. Um, and because charged particles travel freely up and down the field lines, but not freely sort of across field lines, each magnetic field line is an equipotential. So the electric potential is the same along the whole field line. So to get the electric potential in space, what you have to do is trace field lines down to the surface of the ionosphere, work out where they intersect the ionosphere, and that gives you the potential of the whole field line. So this is the Weimer 2005 ionospheric potential model. This is looking at down at I think the North Pole, basically showing a very typical sort of two high potential on one side on that is high potential dusk and low potential dawn. And then you can trace, as I say, you can trace the field lines down to get potential across the entire atmosphere. So that's the U portion. We've got U and B. We'll come back to K because that's a complex one. So at this point, I think I started to add more and more sort of layers to my Python map of different things to call magnetic field models, electric field models, field line tracing, various coordinate transforms and things. And the C types sort of wrapper that I had to convert between Python data types and C data types really wasn't holding up. And so I ended up doing a massive rewrite and refactor the extension of the class that I used to do that. So I ended up with C vectors class. And this effectively was me trying to make sure that if Brad or anybody else wanted to write new methods and then do the interoperability step between Fortran and Python, they didn't have to worry about the various differences between Fortran and Python. So for those of you who are not familiar with either one or the other or both, Fortran arrays are column major and index from 1, with Python arrays are row major and index from 0. And as I was writing this code, that was an enormous source of bugs, so pretty much constant. And to avoid either my future self or anyone else who's writing code from getting these implementation errors from Fortran interoperability, I set up this whole class to try and handle that, to just abstract that layer away. And I mean, previously, all the code I'd written in the rest of my life had just been effectively either a small physical model or plotting the output of somebody else's big physical model. I never really had to write anything that I would think of as an abstraction layer. So trying to make sure that this, was robust, that it was intuitive, and that it actually covered all the use cases that actually needed from it, was a bit of an exercise. And I think possibly if you look through the Git history, this class is the one that has been edited the most. I found this way harder than any of the physical models I implemented, and way harder than the Python wrappers or any plotting code or anything. But it does now. I think it's quite elegant. I think I can get pretty much any vector I can translate between Fortran and NumPy, Fortran and Python without any issue. And it also handles things like arbitrary different page shapes, because for someone who's used to working in NumPy, which is what the Python wrapper really expects, you get all this sort of nice broadcasting behavior that's very powerful. And I didn't get the whole strength of broadcasting into it, but I managed to get most of it, at least for something you assume is a selection of 3 vectors, an array of 3 vectors. I managed to get that broadcasting behavior into this, but it was also a real struggle. Yeah, and it wasn't without issue. So segmentation faults were a new thing for me. I hadn't really used Fortran enough to across them before. And yeah, you don't really get much information on segmentation faults. You just know that things gone wrong. And actually, at this point, I was introduced to Valgrind and GDB by someone else in the space weather community. I still haven't really got to grips with Valgrind, but GDB is very good. So GDB is a graphical debugger for anyone who's not used that before. graphical, not graphical, what's it?
What did you study?
GNU, yeah. There is a graphical interface for it as well that I forgot what it's called, but I didn't get that working in the end. Um, yeah. And the other thing was the first time I wrote the C vectors code, I hadn't really thought too much about the implications of Fortran being column major. And so I wrote my Fortran code, my Python code, to be as easily interoperable as possible without realizing that flipping the way out to represent three vectors in Fortran would be a sort of 20 times speed up. So after I got that working really neatly, my supervisor pointed out that it was probably a lot slower than it should be, and I had to rewrite it all. uh, okay, so with that finally in place, I can start to do some very basic particle tracing. So in this case, I'm just going to show you a couple of plots that show the difference between the different energy ranges and what dominates the motion of different energy ranges. So because the Hamiltonian total energy is the sum of kinetic and potential energy, the electric potential term is much more strongly weighted, effectively, for very low kinetic energy particles. So in this case, this is a low energy particle. The purple path is a low energy particle, and its path is basically determined entirely by the electric potential, which is given by the sort of color scale in the background there. So in this case, we can see this particle follows a sort of potential contour uh, from the night side and out to the day side. High energy particles, on the other hand, the kinetic energy term is much larger than the potential energy term in the Hamiltonian. And so their motion is effectively dominated by the magnetic field. So in this case, the magnetic field is, at these distances, it's pretty similar to dipole, which means that it's basically radially symmetrical. So this particle is just moving around a constant contour of magnetic field strength. And so the equatorial projection of its path here is just pretty much a circle around the Earth. Where things get interesting is the intermediate energy range, where the potential energy and the kinetic energy are comparable to each other in magnitude. And then you have to work out where the particle's going. You really do have to look at the full Hamiltonian of the particle. And so the background color here is the Hamiltonian of this particle in particular. And the path here gives you a constant contour of the Hamiltonian. And this particle is effectively nearly trapped. If it went to slightly higher energy and that gap there closed up, it would become a trapped particle going in a circle around the Earth. But yeah, so this intermediate energy range is of particular interest because it effectively defines where in existing radiation models you have to cut off and say at this point we can no longer ignore the electric field because it's really starting to have important effects. And in the spirit of not really knowing what I was doing in this paradigm, I just plotted lots of different things against each other. One thing I plotted was for loads and loads of different possible particle paths. I plotted the potential energy versus kinetic energy, and it came out with this beautiful sort of fish. And I decided in the end, this hadn't told me anything, but it did look very nice. So I plotted a whole bunch of them and did a little rendering and came up with a little sort of space aquarium of these fascinating shapes. And I still one day really hope to get some like actual physical intuition out of these. But for now, they just look very nice, and I can't resist putting these talks. So they're the fish. Uh, so this is probably the most frustrating part of the development process. So probably about 6 months ago, I came across the fact that the specification for Fortran is not necessarily the same as what your compiler does. Which I guess abstractly, if it asked me at that point, I would have been able to tell you that was the case, but I would never worry about it. But because I was trying to make it open source, I wanted to use something that was an open source compiler, so something like G-Fortran that isn't proprietary, that you don't have to pay for. So I didn't really want to switch compilers, but I came across this horrible thing where, in order to try and make my field line tracing and the manipulation of field lines a bit easier, I converted them all to parameterized derived types, which are part of the Fortran 2003 standard and onwards. It's like a sort of derived type Fortran, something like a class or a struct in other languages. So the parameterized version is on the left, and it actually takes one or a couple of arguments that can decide something like the size of your arrays inside the derived type or the type of them. So if you could say I want it to be this, I want this particular parameterized derived type to be double floating points or integers or whatever. And this is quite powerful because it allowed me to do some customization of stuff like if I want to change the maximum number of points along a field line, I can have that as an argument to the parameterized derived type. Or at one point, I also had like the step size for the or no, the sort of grid spacing size, my field for my particle tracing, and things like that. The issue is that G-Fortran, and as far as I can tell, most Fortran compilers don't fully implement parameterized derived types. They implement them just enough that you won't notice the first time you try and use them. But as you add to your parameterized derived type and try and do more and more things with it, you get increasingly weird bugs because particularly G4tran doesn't fully implement all of their behavior. And somewhat, yeah, I mean, somewhat annoyingly, it's not that easy to know that. You have to go and find bug reports on G4tran forums to actually discover that this is the case. But I guess that's just one of sort of the vagaries of trying to use sort of such a massive and I don't say elderly, but venerable open source project, such as G4tran. Yes, one thing I realized though was that at this point, someone on one of the forums mentioned that there probably should be a warning flag for this. I thought, what's a warning flag? So I turned on all the warning flags like fire. But it solved so many problems. It solved so many problems. It's amazing. Um, yes. Okay. So at this point, we're getting to K, the K in UBK, which is almost the final piece of the puzzle. So K is a parameter of, well, it's a property of field lines, effectively. So it's defined by this integral at the top, which is, so the integrand here is the square root of the magnetic field strength at the point where a particle will reflect back along the field line, so that bounce motion that I mentioned at the start, minus the field strength at any point along the field line. So you integrate along the field line between one mirror point and the other to get K. So K, there's a value of K for every single point on the field line, effectively. And this plot here, on the left, we've got the magnetic field strength along the sample field line and along the y-axis, and then the x-axis is the relative distance limit. So from the North Pole to the South Pole, how far along are you? And then the right-hand plot shows the value of K versus B along this field line. And as long as the field line only has one local minimum anywhere along it, K is really nicely behaved. It's just this nice monotonic function, single valued, very friendly. However, compression of the field on the day side by this stream of charged particles off the sun can result in like quite significant distortion of these field lines, and you can get local maxima along your field line. And at this point, K becomes a really horrible function. It becomes discontinuous, becomes one to many, and yeah, it becomes really horrible to work with. And the reason we need K is that K effectively is a conserved quantity. So particles that mirror at a given value of Bm will always stay at the same value of K as they drift around the Earth. So it's useful to have K as a way of, it's basically the third coordinate we need to describe where our particle is. So we can describe it in U and B and in K, and that gives us effectively a unique description of the path of the particle. So the difficulty is that now we've got this discontinuous one-to-many function, and really we want to be able to interpolate along this curve, which is not particularly easy in this case. Like this introduces a huge number of complexities to interpolation. You need to know which which are the sections of the curve I'm aiming for, where exactly is this continuity, and yeah, which of multiple solutions do I want, and do I want to track them all? Um, so in the case where we've got a dipole, if we're going back to the single minimum, in the case we've got a dipole, we can do that interpolation quite easily, and we can get these surfaces of constant k. So this is looking at the Earth from, you can imagine this from uh, the sun somewhere off to the right, North Pole top, South Pole bottom. You're just looking at the Earth when it feels side on. And the surfaces, there's some dipole field lines at grey. The mouse is on that screen. We get dipole field lines at grey, and a few different constant k surfaces that go up with these sort of curved surfaces through space. And the point is that the mirror points of the particles will stay on these surfaces. If it starts on that surface, the mirror point will stay on that surface as it drifts around the Earth. So this is very important for you to translate from that UV space back to real space and working out where your particles are in real space. And each of these constant K surfaces gets its own area in UV space the particles can remain trapped in. And this is where the sort of real difficulty, this is where I come back to that epigram at the start, where I said everything should be designed top down except the first time. Because at this point, we're really up until now, it's all been established physics explored quite carefully. But at this point, I'm sort of into the wild and doing my own experiments and learning how this physical model behaves. And especially when it comes to these field lines with multiple minima and these you end up with discontinuous K surfaces, and horrible bits of mapping between physical space and UBK space. And the difficulty with that is that I don't know how to structure my code as I'm writing it, because I don't know what I'm going to do with it in the future. And I think really this has been the greatest problem I've had, is how to design software when you don't know entirely what experiments you'll want to do with it in the future. And I think a lot of the decisions I made throughout this project have been very useful in getting to this point, but I'm now realizing that that they're holding me back in some sense when I'm trying to deal with these particularly complex problems. For instance, the way I've structured field lines only really didn't really allow for distinctions between different continuous regions of this BK relation. So actually, I'm sort of in the process of working out if I can rewrite my field line tracing and sort of memory handling code to allow the multiple solutions to this relation. But then the problem is I built so much stuff on top of the field line tracing that suddenly trying to fit in these extra solutions in this non-continuous K space has been pretty horrendous. So yeah, from a software engineering perspective, I'm still working on that. From a research perspective, because I've got my two hats on, I'm still trying to publish papers on this. I've quietly ignored it and just said, I'm not going to think about field lines for multiple minima. I'm going to restrict myself for the first couple of papers I try and write to simple magnetic fields where you don't encounter these field lines. But yes, I mean, when I finish the papers, I've got this problem waiting for me. And I was hoping I'd have some sort of inspiration, whilst I wasn't really thinking about it, but it's yet to happen. But yeah, it's going to be interesting to see what I have to do to make the software work, and also to then reflect on that afterwards about what I could have done potentially when I did write it the first time round in preparation for this. Like, was there anything I could have known if I'd stopped thought about it in the right way? So the last thing I wanted to mention was performance is obviously a key issue in any large numerical model. This is an email I got, a section from an email I got yesterday from my master's student, who is the third person to use this code. And he says, I suspect there's also much room for optimizations. A very simple field line tracer I've sketched out is already at over 10 times the performance of UBiKuity. Which is lovely. It's a bit of a blow to the ego, if it's true. But it's also great news, because if I can get 10 times speed up, um, from a master's student who's been working on it for a week, then what can I do if I stop and think about it for the next few months, or if he stops and thinks about it for the next few months, Um, yeah, so I think to salve my own ego, I'll say that I haven't thought that much about performance so far. Most of my sort of planning has been around um, documentation, ease of use, and ease of development and sort of extensibility. Um, because I think somewhere in the back of my mind, I've heard somebody say that thermodynamic optimization, it's something is a terrible idea. There's some sort of nice saying there, but I can't remember it now. Okay, so in conclusion, on the right there, I found on my desk, on the giant pile of drift papers on my desk, the very first design diagram I ever drew for this code, um, which I think I planned before I even started the job, just when my supervisor had described it to me. Um, I have kind of stuck to it in some ways, interpreted generously. Um, but yes, I think the points I wanted to make really are that the nature of model development um, means that if you're developing a model the first time around, it's nearly impossible to actually get, well, for me at least, it's incredibly difficult to get scientific software design right the very first time around, just because you don't have a well-constrained problem, really. If you don't know necessarily exactly how or what you're going to do with the software or um, how you need to behave, then designing it the right way is, it's a shot in the dark, really. Um, and the reason for that is really that the insights of the physics do change what your requirements are. It's a learning process writing these models. And yeah, as you learn new physics, as you learn new or find new things you want to do with it, it's naturally going to change what you need the code to do. Um, and I guess this didn't come entirely as a surprise to me, but I guess the magnitude of it came as a surprise to me. The amount of time it takes to convert working code into something that is shareable and extensible and reproducible, or even to write it that way the first time around, is a really enormous additional workload. And I think really, in my experience, the current sort of funding ecosystem and what's expected from researchers doesn't really reflect that. In the amount of time and effort and money that it costs to do things properly in terms of writing large code isn't really accounted for in what you can get funded for. So, um, yeah, I think I'm going to wrap up there. If anyone's got questions, I'm going to take them.